Moving on to number 11, or gravity stuff. At point X, shown midway between the centers of these of two isolated planets of radius r and 2r, the net gravitational force on an object is 0. If the mass of the smaller planet is m, and the mass of the larger planet has to be, well, that means that there's an equal gravitational force from each planet here, if the net force is 0. So there'd be a force on here from this planet, and there'd be a force this way toward this planet, and they must be equal. Well, universal gravitational force is gmm over r squared. So let's say the mass of this is little m, not that it matters. So these two forces must be equal. So the force from this one is g m over r plus, and I don't know, all I know is that it's midway, right? So I don't know what this distance is here. But if I call this whole distance here, I don't know, we could call it, is it too confusing if I call it x? Then that whole distance here, let's call it x. So x squared. And that's got to be equal to g, and then the mass of this one is what we don't know, right? That's the mass of the second planet. I'm trying to solve for that. M over, and then this distance here, so let's see, x is this distance, and x is also this distance. Right? So let's look at what cancels out. So the radii of the planets actually doesn't make any difference, does it? So the masses cancel, the x squareds cancel, the g's cancel. So the m2 must just, in fact, be equal to m. The masses are equal. So that's reminding us that it doesn't matter how that mass is distributed throughout here. It could be all concentrated at this point, and that's the very same. So they have to be equal. Number 12. A particle moves along a straight line. Its speed in meters per second is given by this. How far does the particle move between time 1 and time 2? Hey, that's a calculus problem. You want to know how far something moves? It's a displacement. Then you do this. And even though your calculator's loud, it's not going to help you much here, is it? Antiderivative here of a is at. Antiderivative of bt squared is bt cubed over 3. And I want to do that from 1 to 2. So let's see. So plugging in the 2, I get 2a plus 8/3 b minus a plus 1/3 b. So 2a minus a is a, and 8/3 minus 1/3 is 7/3 b. That looks like d. That's a calculus problem, isn't it? This is calculus-based physics. Ball is tossed and follows the trajectory shown above. So it's projectile motion, horizontal velocity is constant, and constant acceleration in the downward direction. So its acceleration is constant. It's downward, 9.8 meters per second squared. Its speed is constant? Nope. Horizontal component of its velocity is 0? No, it's got constant horizontal velocity. That's wrong. The vertical component is at a maximum? No, the vertical is 0 here, right? Because the velocity there is all horizontal. It's just the constant horizontal velocity. And kinetic energy is at a maximum? No, actually it's at a minimum there, right? That's when it's going the slowest, because everywhere else it has some component of vertical. So it slows down to the constant horizontal velocity and then continues there. So that's B. Number 14 looks like momentum problem. As shown in the figure above, a child of mass 25 kilograms running at a speed of 3 meters per second jumps onto a stationary sled of mass 5 kilograms on a frozen lake. The speed at which the child and sled begin to slide across the ice, so momentum is conserved. The momentum before is the kid. The momentum after is the kid and the sled. I don't know what their final velocity is. It's 75 over 30. And that's, let's see, 15 goes into both of those, so that's 5, 2.5. That's the kind of speed you want to deal with these with, right? More momentum, looks like. A block of mass m is initially sliding, makes an elastic head-on collision with another block of mass 2m that's initially at rest. So the momentum before is equal to mv sub 0. Right? That's the only thing moving. So that means the mass afterwards has to also be equal to that, right? And also, since it's elastic, kinetic energy must be conserved. So I'm going to do a quick calculation and see if I can eliminate some of the answers just by seeing if momentum is conserved. So here, momentum, this would be afterwards, that's mv sub 0 over 3, and this is 4 mv sub 0 over 3. That's too much. If I add those together for momentum afterwards, they're both in the same direction, so that can't be right. This looks like it could be, because I have negative mv over 3 and positive 4 mv over 3. So that does add up to 1. So far that's okay. Here, that also multiplies out, so that would work for momentum conservation at least. This one would not, because this is going to give me mv sub 0 here and then minus something here, right, because those 2's will cancel. So no, momentum is not conserved there. Here, similar problem. The 2's cancel. I get mv here, but I also have some momentum here. So these two are the ones where momentum is conserved. Now we have to see where kinetic energy is conserved. So is kinetic energy conserved here? Let's see. The total kinetic energy beforehand is 1/2 mv squared, right? So it's got to add up to that. So here I've got 1/2 m times v squared, which would be v squared over 9. So that's 1/18 mv squared. And then here I've got 1/2 m v squared, and the v squared, that's going to be 4 v squared over 9. Those cancel out, so I have, let's see, let's do that in 18ths too. That's 8/18ths of a v squared. If I add those together, I get 9/18ths. That's 1/2 m. So that works. Kinetic energy is conserved there. And you can check this one. It is not conserved here. The correct answer is B. Number 16. 2 kilogram mass is attached to the 0 centimeter mark and a 3 kilogram mass here. Center of mass of the combined system is located where? Well, you think it'd be somewhere like here-ish. So maybe one of those. Definitely not here, right? Because the heavier object's here. So let's see. We do 1 over total mass times, if I take this to be x equals 0, then I have the mass there times its location, and then the mass here times its location at 100 centimeters. So that's 300 divided by 5, that's 60 centimeters. The answer is C. Number 17. Mass attached to a vertical spring, the displacement of the mass is given. At what time does the mass experience a maximum positive acceleration? So This is the positive direction. So maximum positive acceleration. Well, when it's here, that's maximum displacement. That's going to be maximum force and therefore acceleration toward equilibrium. And here, this is where it's going to be maximum force and therefore acceleration upward. Right? You could also just think about taking two derivatives of this, and then the second derivative would be an upside down version of this. That also gives you a maximum there if you want to think about it that way. But anyway, it happens at time 3. Number 18. For an object in simple harmonic motion with an amplitude A, the kinetic energy will equal the potential energy when the displacement is. So the kinetic energy, which is 1/2 mv squared, is equal to the that's the kinetic is equal to the potential energy in the spring, which is 1/2 kx squared. So when are those two equal to each other? Well, when they're half and half, right? When they're half of the total energy. And the total energy is equal to 1/2 ax squared. Right? So half of this, if you want half of the total energy to be equal to we want to know when does that happen. So, oops, sorry, I messed that up, didn't I? I meant to say k. That should be ka squared. The k is still k, of course. And we're talking about the maximum displacement. The total energy is equal to the energy when it's at the maximum displacement. It will only have spring energy, and it will have a velocity of 0. Sorry about that. So when I set this equation, 1/2 the total energy is 1/2 k a squared, right? So I want to know if I borrow some room down here, 1/2 ka squared equal to 1/2 k x squared. Where does that happen? Well, the 1/2s cancel, and I just get, oh, sorry, I went 1/2 of that, so this needs to be 1/4 here. So the 1/2s don't cancel. Let's multiply through by, we could cross-multiply, let me write that again. Sorry. So when half the total energy is in the spring, right, that's what this boils down to. So I'm going to multiply through by 2, because I want to solve for x. The k's cancel. Multiplying over here by 2, that'd be 1/2 a squared is equal to x squared. So x is equal to a over the square root of 2. Right. Number 19. Examples of simple harmonic motion include which of the following? A mass hanging from a spring moves up and down in a uniform gravitational field. Yep. A puck on an air table bounces back and forth between the walls. That's not, because there's no restoring force. It's just bouncing back and forth like clack, 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 and it would go at a nearly constant velocity between them. A ball bounces up and down on a table. No. We need it for simple harmonic motion. We always need something where there's an equilibrium position and a restoring force. Right? If you're on this side, it pulls you back this way. If you're on this side, back this way. So a spring, a pendulum, physical pendulum, torsion pendulum, those are all examples of simple harmonic motion. Number 19, two blocks are stacked up on top of each other like this. The top block of mass m is attached to a rope that pulls to the left with tension T1. Bottom block of mass 2m is attached to a rope that pulls to the right with tension T2. The coefficient of friction between the two blocks here is mu. Blocks are at rest relative to each other and move to the right at a constant speed relative to the frictionless surface. So what are all the forces here? The forces on T1, forces on M, rather. What are those forces? I have T1, and a frictional force. Right, and those it's moving at a constant velocity, so those have to be equal to each other. And here, big mg and a normal force there. Big mg. And this would be mu mg. Right? And then for the other block, we have, we wanted to make a force diagram of that. 2mg. I also have mg weighing down on it, right? The normal force from the surface would have to supply a 3mg force. It's really supporting both of those, right? And then I have this pulling force T2, and I have this frictional force. But notice this friction, there's only one interaction between these two blocks. There's only one frictional force here. It's friction between those two. This is a Newton's third law, equal opposite pair. There is only one friction between them. So if those two are equal, and it's moving at a constant velocity, then T1 and T2 have to be equal, because those are both equal to that friction force. And I guess we already answered this question, didn't we? There's only one frictional force. It's a mistake to think that there's two different frictional forces. So we went up to 21 there because those were related to each other. We'll leave it there.